This video is on the preparation of ethers. Ethers are a relatively unreactive chemical and therefore they tend to be used as solvents for fats, oils, waxes, and on an industrial scale found mostly in the cosmetic industry or the flavor industry. They are also omnipresent in nature in all kinds of forms, but the ether is not usually the key part of the molecule. Ethers are most readily made using alkoxide ions or alcohols as the nucleophile, as when these act as a nucleophile you're forming an oxygen-carbon bond, and as there already was a carbon-oxygen bond you end up with your carbon-oxygen-carbon ether. When an alkoxide is used as a nucleophile, it is called a Williamson ether synthesis. For example, here we have sodium ethoxide, the ethoxide anion reacting as a nucleophile on this ethyl bromide to yield us diethyl ether in an SN2 reaction. As the basicity of alkoxide is similar to that of the hydroxide, the same arguments apply for SN2, i.e. they're good for primary carbons or non-bulky secondary carbons. We can't do it on tertiary carbons, and on unfavored secondary carbons we can very likely expect elimination reactions instead. So how do you make alkoxides? Well, we obviously have to deprotonate an alcohol. Usually this is achieved by using sodium metal. If we mix the alcohol with sodium metal, we end up with the sodium alkoxide salt and hydrogen gas bubbling off. This is a very clean reaction. Phenols are more acidic, therefore we do not need to use sodium. As it's a strong base, we can use something milder, such as sodium hydroxide. These sodium salts are usually made in situ or in the same reaction vessel as you are doing your main reaction, so often you will see a question that looks something like this, where there are two steps. Well, clearly the first step is just adding sodium, i.e. we're going to deprotonate the original alcohol, and step 2 we are adding our alkyl halide for the Williamson ether synthesis. Now you have a go. You may pause now, and these are the answers. Most unsymmetrical ethers can be made in two different ways, as seen here. Usually the route with primary halides will give higher yields because it's easier to perform SN2 reactions on those positions. You have a go. Look at these two reactions. In the first one, predict which reaction would proceed faster or is just a better method. And in the second, predict the product and state which of these two methods would be better. You may pause now. And here are the answers. As mentioned earlier, ethers are also prepared with alcohols as the nucleophile. In this case, as you would expect, this is not a very good nucleophile, so you would expect this to be more of an SN1 type reaction. For example, we can have this tertiary alkyl halide reacting with ethanol to provide us this ether product. However, it is not always just tertiary alkyl halides that we have to worry about. If we have acidic conditions, we also need an alcohol, as the alkoxide cannot coexist with acids. Right? Any alkoxide is a strong base. You put it anywhere near an acid and it will do acid-base chemistry instead. So for example, if we're trying to react two alcohols together, we'll have to do it under acidic conditions and we will see SN2 chemistry instead. Your turn. Draw the expected products for the following reactions. You may pause now. And here are the answers. Cyclic ethers can be made by intramolecular SN2 SN1 reactions as long as the ring size is 3, 5, or 6 membered. So for example, if we take this alcohol with an alkyl halide, we can add a base and we can deprotonate the alcohol and cause a ether to form. You have a go. What would be the product of this reaction? You may pause now. And here is the answer.